Me few questions. Answer me few questions. Are you ready to answer? Okay. So, in series combination, which quantity remains constant? Answer quickly. In series combination of resistors, which quantity remains constant? Anyone? Am I audible to you? Am I audible? Say yes or no. Okay, I think everything is clear now. Just give me a thumbs up that my voice is clear. Okay. So if we move up for today's topic, let's see. Now today we will start with what is cell and what is EMF. Whenever you see questions in current electricity chapter, there is a cell and which has written some EMF kind of thing. So what is EMF? Listen to me. Try to remember each of the things that I am telling you. Listen. If you see the definition part, full form of EMF is electromotive force. Electromotive force. But it is actually not a force, it is work done. What it says, work done by the battery. Let's suppose if you have seen there is a battery. If I represent the battery, it has two terminals like this. This is the representation of a battery. Can you just give me 1 minute? Battery has two terminals. Let's suppose this is terminal A, this is terminal B. That definition says work done in moving a unit charge, like this is a unit charge, from one terminal to the other is called electromotive force, is called EMF. Work done by whom? Work done by the battery force. So try to remember the definition. Work done by the battery force in moving a unit charge from one terminal to the other is called electromotive force. Is it clear? And when this charge is moving inside the battery or in, then the electrolyte which is already filled in it, which has some ions, positive and negative ions, offers some resistance to the flow of charge. And this resistance is known as internal resistance of the cell. This resistance is known as internal resistance of the cell. So two things are clear. What is cell? It converts chemical energy into electrical energy. What is EMF? Work done by the battery force. What is internal resistance? The resistance offered by the electrolyte of the cell is called internal resistance. These charges are moving from one terminal to other, and the other charges are opposing it. Clear? Now, how this internal resistance is represented? It is represented by small r. In a circuit, you can see that, for example, EMF is denoted by E, something like that. Okay. In a circuit, the representation will be like that. A cell will be written, drawn here, and it is mentioned something as E comma R. E comma R. Or for example, if I say, it will be like there is a cell, there will be 4 volt, 1 ohm. So whenever you see something like that, you should understand that this 1 ohm is the internal resistance, 4 volt is the EMF. And whenever you see, whenever you see a representation like that only, like this is 4 volt only, and nothing else is written here, then what does it mean? It means that the battery or the cell has no internal resistance, and such a cell is known as ideal cell. Such a cell is known as ideal cell. So this is the representation of ideal cell, which has R equals to 0. So I think 2 or 3 things are clear here. What is the representation? In general, whenever you see some representation like this, that means this cell is ideal. Whether it is mentioned or not, cell is ideal. Now, how you represent the internal resistance? This is the representation that will be in your question paper. Now, how you will represent it? Let's see. You have to represent it like that. This is 4 volt battery. 4 volt is the EMF. And the internal resistance which is mentioned here, you need to fix it with the negative terminal. I am not saying specifically with the negative terminal. You can fix it to the positive terminal as well. But you need to fix it like that. In this way, you will be able to minimize the error, minimize the errors that will be caused by the sometimes I have seen that, or I can say most of the times I have seen that in a question, students forgot about this 1 ohm resistance or this internal resistance. So try to put it here always. This is how you will do. I think everything is clear till now. Okay. Internal resistance part is done. Now there are few things that you should remember. One more thing, that is terminal potential. What is terminal potential? These are two different things, EMF and terminal potential. What it says, the potential difference between the two terminals of a cell is called potential difference. I think it is clear. Definition part is clear. The potential difference between the two terminals, cell is like that. The potential difference, this is terminal A, this is terminal B. The difference between these two terminals is called potential difference. Okay, I think this is Vinay. Vinay, this is current electricity which is going on. Actually, in yesterday's class, it was left. So we are covering the leftover portion, and tomorrow's class, we will cover magnetic effect of current. Clear? Okay. From YouTube, mark your attendance, everyone who is present. For open circuit, now these are the punchlines. Listen to me. These are the important things. What is the meaning of that? For open circuit, like this. For example, this is a cell which has some internal resistance, and this is some external resistance R. This is R, this is E, and this is a switch. Now, until I connect the switch, this circuit is open. So in this situation, what is it? In this situation, terminal potential is equals to EMF. In this situation, terminal potential is equals to EMF. Write it down. Students, please write it down because these are the important things. Next thing, if battery is discharging, or you can write it as cell is discharging, whatever you may write. If cell is discharging, then terminal potential will decrease by IR. V is equals to E minus IR. How you will identify that cell is discharging? Like this. If I connect this switch, this is ER, this is external resistance. Now, as soon as I connect this switch, you can see that current will start moving in this direction. And what is the identification of discharging? When current is coming out from positive terminal. Are you able to see? When current is coming out of the positive terminal, this is known as discharging of the cell. What is the purpose of charging? How you can identify the charging? Like in this circuit, you can see, I can draw. Suppose this is a cell. This is another cell. This is some resistance. Like suppose in this circuit, current is moving like that. Now you can see what I have told you, that whenever current starts from positive terminal, it is moving away from positive terminal, this cell is discharging. But you can see that this cell is charging. So what is the identification of charging of a cell? It is when current enters from the positive terminal of a cell, then it means that cell is charging. If current leaves from the positive terminal, it means cell is discharging. So can you identify charging and discharging of a cell? At least say yes or no. Can you identify which cell is charging, which cell is discharging? If I can ask you, okay, very good. If I can ask, tell me about this cell, whether it is charging or discharging. Okay. I am not drawing complete part. From this part, can you identify whether it is charging or discharging? This is a part of some circuit. If someone has asked if there are both charging and discharging, then is it charging or discharging? The question is not that much clear, but what I got is, if both charging, if there are both charging and discharging, then is it charging or discharging? Okay, in a circuit, if two cells are there, then for sure, one thing is for sure, that at least one of them is charging and one of them is discharging. So what you write, okay, I understand your question now. For example, this is cell E1 R1, this is E2 R2. So you are saying how we can write the terminal potential. That's what you are writing now. Terminal potential is represented by V. So how you can write terminal potential for this cell? Okay. For this cell, you should write V1 is equals to, this is charging now, E1 plus IR1. E1 plus IR1. And for this cell, this is discharging. So you will write its terminal potential as V2 is equals to E2 minus IR2. Is it clear now? Because we need to write the terminal potential separately. This is for first cell, this is for second cell. And in both the cases, you need to identify which is charging, which is discharging. I think it is clear now. Moving further. Very good, Veena. Okay, Veena is here. Yesterday, I have told about Veena. What is Veena? Anyone remember? So now we are going to discuss about combination of cells. Combination of cells, we will study about two combinations. One is series and one is parallel. Identification is again very similar. What is the identification for series combination? Back-to-back connection without any junction. This is E1, this is E2, R1, R2. And these two cells are connected externally with the resistor R. Clear now? This is the situation for series combination. This is back-to-back connection. Okay. So for this situation, you need to remember the relation. What is the relation? What is the equivalent resistance? Small r, whenever I am writing small r, it means it is internal resistance. So equivalent internal resistance will be R1 plus R2 because this is a series combination. This is a series combination. This is clear. Another thing, what will be the equivalent EMF? Equivalent EMF will be E1 plus E2. E1 plus E2. Now listen to me. This is the simplest thing that I am telling you. Now there might be some exceptional cases like that. You can see here, the direction of cell in both the cells is same. That means positive is in the same side. Positive terminal is on the same side. But sometimes the things may be different. And in that situation, the things may look like this. Again, they are in series. Again, they are in series, but there is a difference. The polarity of the second cell is inverted. Polarity of the second cell is inverted. So now what will be the case? You can write it as E equivalent is equals to E1 minus E2. E equivalent is equals to E1 minus E2. This is known as supporting series combination. This is known as opposing series combination. These two cells are opposing each other and these two cells are supporting each other. So this is known as supporting series combination. Supporting series combination. And this is known as opposing series combination. Clear? Now I will give you a few examples of situations, how you can solve it. Listen to me. Before going to the parallel combination, listen to me. I am giving you some simplest of forms like this. Let's suppose this is 5 volt, this is 10 volt. Clear? Then what will be the equivalent EMF? Can you identify whether they are supporting each other or opposing each other? Whether they are supporting or opposing each other. Answer very quickly. Your energy is low. Someone has answered. Supporting, very good. Sushant is very good. So they are supporting. So equivalent will be their addition. That will be 15 volt. That is clear. Now, how will you represent this combination? It can be represented as 15 volt. So this combination is equivalent to this resultant, this equivalent cell. Now, again, if I ask, I'm writing it in a congested manner. I hope you are with me in this situation like that. So you can understand whatever I am writing. Listen, let's suppose in the same diagram above, if I can change the polarity of the other, this was 5, this was 10. Now you can see that they are opposing each other. Then what will be the equivalent EMF of this circuit, of these cells, this combination? You will say the combination will be -5. Very good. So what is the meaning of -5? You can subtract. Everyone should listen. 15 volt. Very good. Supporting Veena. Neil Patel is also saying supporting. Very good. Okay, -5. Everyone is saying -5. So now -5 is a correct answer. Now listen to me what I am trying to say here. That you need to subtract larger EMF and lower EMF. So that will be equivalent will be 10 minus 5. It is 5 volt. No, you are not wrong. I am also not wrong. What I will do here, the resultant EMF, which cell has larger potential or larger EMF, you will say this cell has larger EMF. So the equivalent cell that I will draw will follow the polarity of the larger cell. Can you see that? What I have done, there were two cells, 10 and 5. The resultant will be the difference of the two, and the polarity of the equivalent cell will be similar to the larger cell. In that situation, I have put the polarity of the cell, that means plus here, minus here. So I don't need to put -5 here. And this is my recommendation to you. Don't put -5 as a potential. What you should follow, just draw the equivalent circuit by following the larger cell. Because in some large questions or some lengthy questions, you will forgot that minus sign, or you will create some error with this -5 sign. Minus sign, you will create some mistakes. So for that, try to do what I'm trying to say. Just follow the polarity of the larger cell in your equivalent circuit. Is this thing clear? -5 is also correct. There is no problem with that. Clear now? Should I move further? Yes, sir. Very good. Okay, moving further. So there is again a parallel combination. Identification is again similar. What is the identification of parallel combination? Two cells are connected between two same points, like this. AB, this is E1 and R1, this is E2 and R2. What is R2 and R1 here? R1 and R2 are the internal resistances of the cell. For ideal cell, what is the value of internal resistance? You will say 0. Clear? Okay. Now parallel combination. So two things we can do here for parallel combination. What will be the equivalent internal resistance? You will say 1 upon R equivalent is equals to 1 by R1 plus 1 by R2. This is the series parallel combination, and this is the similar to the parallel combination of resistor. Now, what will be the equivalent EMF? So this relation is not very simple, but I will make it simple for you to remember. Remember the form I am telling you. E equivalent over R equivalent will be E1 by R1 plus E2 by R2 plus so on. This is very simplest form to remember. E equivalent by R equivalent, E1, R1, E2, R2, similarly, so on, so on, so on. If in any part I change the polarity of one of the cell, then you need to put a negative against that cell. For example, if I draw it like that, so there are three cells you can see. E1, R1, E2, R2, E3, R3. This is very famous question. So what will be the E equivalent in this situation? You should write E equivalent by R equivalent is equals to E1 by R1 plus E2 by R2, and the polarity of this cell is reversed. So you should write minus E3 by R3. That's it. Clear? Now R equivalent you can calculate easily by this formula. So I think everything is clear. Remember this. Remember this. Okay. So I think in the next slide, there will be a question. Okay, I will repeat. Which part you want to repeat, Millie? I think you want me to repeat this question now? Okay. Whenever you see parallel combination of multiple cells, then the relation is this one. We know this relation. I have try to write it in a simplest way. You can remember this relation. Now, what is the problem? What is the exceptional case? Or you can say, this is not the exceptional case. This is the simple physics. You can drive it in later stage. That if the polarity of a cell is reversed, then what you need to do, you need to put a negative sign against it while writing the equivalent equation. Just put a negative sign against it, nothing else. Clear? Okay. Now, so there is a one more relation that you should remember. I hope you know the relation between small r, EMF, and terminal potential. Can everyone identify each of the terms? V is what? Terminal potential. E is what? EMF. R is what? Internal resistance. What is the relation between all these three quantities? So the relation is, you need to remember, write it down in your notebook because we are going to use this relation. R is equals to R E by V minus 1. Someone might say, sir, you are forcing us to remember a lot of things. But students, this is necessary thing. You should know these things. What is R? Internal resistance, external resistance, EMF, terminal potential, and what do you say about one? One is one. Okay. I think clear. So now I am going to give you a question. Try to solve it. Try. Try with me. Okay, just tell me. How many of you are sitting with pen and paper, or you are just lying on your bed or whatever you are doing? How many of you are sitting with pen and paper and trying to write down the things? Very good. Only one person from YouTube. No one is holding pen and paper. Okay. Very good, Sushant. Chandana. Okay. So, okay, one more person. Very good. So question says, for a cell, terminal potential difference is 2.2 volt. Listen to me very carefully. When the circuit is open. Now identify this line, this statement. What is the purpose of this line? Terminal potential, they are saying how you represent terminal potential. You know, the representation of terminal potential is with V. So this is V. V is equals to 2.2 volt. When circuit is open. Now, as soon as I add this statement that circuit is open, what does it mean? I have told you that for open circuit, EMF is equals to terminal potential. I have written it. For open circuit, V is equals to E. That's what we have studied in our punchline. That was the first punchline. Is it clear? So we can understand here that EMF is also 2.2 volt. Statement is very much clear. Now again they are saying and reduces to 1.8 volt when cell is connected to a resistance of 5 ohm. Now they are saying that external resistance is 5 ohm, and when circuit is closed, its terminal potential becomes 1.8 volt. You need to find the internal resistance. You need to find the internal resistance. So what is the relation between E, V, and R? You can say that the exact relation I have written on the previous slide, that was R is equals to R, E by V minus 1. Can anyone solve this relation? R is equals to, capital R is 5, E is 2.2, V is 1.8 minus 1. I think you can solve this. I don't need to solve it out. You can solve it now and you will get some answer. Okay. Answer is A. Okay. Very good. Answer is A. Sushant, very good. Okay. How many of you are able to identify that this is E and this is V? If you can do this, the question is very simple to you. Clear? Moving further. Kirchhoff law. This is the backbone of this chapter. Kirchhoff law. Okay. Now listen, it will take some time. Okay, just give me a Vina. Vina. A. A is the correct answer. Okay. What is junction law? Kirchhoff has given two laws. One is junction law, one is loop law. What is junction law? It says the current entering a junction is equals to current leaving the junction. Current entering the junction is equals to current leaving the junction. So you can identify the junction in this circuit, in this diagram. This is the junction. So current entering the junction is I1 and leaving the junction, two currents are leaving the junction. That is I2 plus I3. This is what our Kirchhoff junction law. On which principle it is based? It is based on conservation of charge. It is based on conservation of charge. This is again an important question. On which conservation principle it is based? It is based on conservation of charge. Junction law is very much clear. Can someone answer me? I am drawing a simple question. Okay, let's suppose this is a current I. This is a current I1. Then what will be the current in this arm? What will be the current in this arm? Can anyone answer? Can anyone type in the chat box? Quick, quick, quick. I. Deepak is saying I. Anyone else? Anyone else? Quick. You are very slow in typing. I2. Okay. Okay. I2 is a good thing. We can write it here I2. What is the value of I2 in terms of I and I1? We know the two terms. I have given you two terms. Remember one thing. If I am asking something, then it shouldn't be a variable. I have given you two terms, I and I1. Then answer should be in terms of I and I1. Very good, Veena. Veena is correct. I minus I1. Very good. Because what you can see, you can apply Kirchhoff's junction law here, or it is sometimes called as KCL, Kirchhoff current law. I minus I1, Ritu and Gauri Lakshmi, both are correct. So what will be the current in this circuit? In this part of the circuit is I minus I1. I current is coming from this side. I1 is left there. So what is the remaining current? I minus I1, that should go there. Very good. Very good, Deepak. Okay. I think it is clear. Moving towards the Kirchhoff voltage law. Next slide. This is loop law. Sometimes it is called as KVL. What is the statement? Anyone know the statement? The statement says the algebraic sum of potential differences in a loop is zero. The algebraic sum of potential differences in a loop is zero. This is again a very simple statement. For example, what I say, listen to me very carefully. Someone might confuse with it. For example, this is a circuit like this. This is a cell. This is one resistor, another resistor. I am drawing a simplest form of circuit. Okay, tell me one thing. Do you want me to tell you or to teach you how to apply loop law, or all of you are aware of that? Because it will take some time. It will take around 5-6 minutes to complete. If the concept of KVL is clear to you, then I can skip it. Comment quickly. Okay, I will teach. I will teach. Okay, listen. Now, what you need to do, the statement says, let's suppose this EMF is Z. The statement says algebraic sum of potential difference in a loop is zero. What you need to do, select a loop. This is a loop. You can identify the loop. Na? The loop is something which starts and ends at the same point. Let's suppose this is A, B, C, D. So loop is starting. You can say that loop is starting from A, B, C, D, and again coming to A. So what you need to do, just stand at one of the corners, like you are standing here, and complete a circle or complete a revolution around the loop in either clockwise direction or in anti-clockwise direction. Listen to me very carefully. What I am trying to say, just sit or stand at one of the corners. This is the imaginary thing. You can't sit actually, but stand there at one of the corners and revolve around the loop either in clockwise or in anti-clockwise direction. And while moving, write down all the potential differences that you face. Write down all the potential differences that you face, and the sum of these potential differences is going to be zero. Remember this thing. Now I will tell you some basic punchlines, some basic sign conventions. What are those sign conventions? If you see there is a potential drop, then write it as positive. If you see there is a potential rise, write it as negative. Someone might have studied it in a different way, but try to learn in this method only. What is the potential drop? If you find a potential drop, write it positive. Rise will be written as negative. So there might be a confusion in your mind. I will clear it in the next slide. Okay. So for example, when you are going from A to B, when you are going from A to B, what you will find? You will find a resistor. You will find a resistor. So across a resistor, there will be a potential drop of IR. You know that potential across a resistor is what? IR. This is Ohm's law. This is Ohm's law. So that's what I have written here. Now listen. This is you moving from A to B. The symbol says you are moving from A to B. Current is moving from A to B. In yesterday's class, I have told you that current moves from low potential to high potential or high potential to low potential. Can anyone answer? A or B? Current moves from high to low or low to high? Right, right, right. Anyone who has taken the class yesterday? Okay. High to low. Very good. That means point A is at high potential. B is at low potential. Is it clear now? Because current is moving from A to B. That means A is at high. Sushant, high to low. Very good. What does it mean? It means that while moving from A to B, you are moving from A to B, potential will drop. Potential is dropping. And what I have told you, you need to write potential drop as positive. So you can write the potential drop, that is delta V is equals to positive I into R. So for this part, potential drop is positive IR. Similarly, in this part, can you identify which is high, A or B? You can say, sir, B is high, A is low. And you are moving from low to high. This is you are moving from low to high. So what you can write here? Delta V is equals to minus IR. Clear? So what you should remember, the memory thing, you are not going to do this all the time, high, low, high, low. So what you should do, how will we know whether we are moving from high to low or low to high, low to high? That's a very good question. Listen to me on the previous slide. Okay, go here. Okay, what I have told you that you should start from any one point and move either in clockwise direction or in anti-clockwise direction. That's what the case now. So whenever you are moving in the direction of current, this is the battery. Can you say that this is the direction of current? From positive current will start. So whenever you are moving in the direction of current, that's what I am saying. When you are moving in the direction of current, potential will drop. When you are moving opposite to the direction of current, then potential will be rising. Rise in potential. So what you should remember, that's a tricky part. Whenever you are moving in the direction of current, write it as positive. Whenever you are moving opposite to the current, write it as negative. Two things are clear. Third thing, this is the case for resistor. Now, what you can encounter while passing through a circuit, you can encounter with a cell. You can encounter with a cell. In that situation, whenever you enter the cell from the positive side, the potential difference will be positive. Whenever you enter the cell from the negative side, the potential difference will be minus E. Four statements that I have told you. Remember, I am repeating it once again. If you are moving in a circuit, in a loop, then two things you may face. One is resistor, another is cell. So for resistor case, if you are moving in the direction of current, then you should write it positive. When you are moving opposite to the current, then you should write it as negative potential drop, negative potential difference. In case of cell, when you are entering the cell from the positive side, write it positive. When you are entering the cell from the negative side, write it as negative. Now I will give you an example. Try to remember all these four statements, take a screenshot, do whatever you want to do, because in the next slide, I want you to respond very quickly. So this is something different. It has a lot of cells. This is the most confusing part. Okay. Okay. Now listen. What I'm saying, we need to apply Kirchhoff law in this circuit. I have taken a different color pen. So you can see there are three cells, 1, 2, and 3. First thing that you should do, identify the larger cell. So this is 10-volt cell. This is 10-volt cell. From the positive of this cell, start a current. Let's say this current is I. Listen every word because you should learn these things. Now, as soon as this current reaches this point, can you see that there are two paths for the current? One is going in this direction, one is going in this direction. Clear? So I can say, let's suppose current I is started from here. Let I1 is there. Then what will be the current in this branch? You will say I minus I1. Is it clear now? I1 is there, I minus I1 is there. Can you see that at this point current will divide or not? Is it a junction or not? Is it a junction or not? No, sir, it's not a junction. That means current will not divide here. Very good. Very good. Everyone. Okay, someone is saying it's junction. Sushant, it's not a junction. Junction is the point where current can divide. If current is coming from this side, where can it go? It have to go there. It has to go there, na? So that means current will not divide here. Current will go same. Similarly, I1 current will come here. I1 current will come here. And both these current meet at this point. I minus I1 and I1. When these two meet, then again there will be a I current back to the cell. Okay. So first of all, what we have done the current distribution part. From which cell? From the larger cell, we have started a current and distributed it in the circuit. Now another thing is, try to apply KVL. So how many unknowns are there? You can see that one unknown is I, another unknown is I1. So only two unknowns are there. So we will make two equations. Like this is point A, B, C, D, E, F. Identify a loop. I will say for loop. Let's suppose A, B, C, D, A. A, B, C, D, A. Can you identify this loop A, B, C, D, A? I am applying Kirchhoff law in this direction. I wrote E twice. Where? Where? Okay. Very good. Very good. Is it clear now? Okay. So what I am saying that I am going to apply Kirchhoff law. Now listen to me. This arrow indicates you are moving from A to B. This is the path. A, B, C, D, A. I am moving in this path. So while moving from A to B, this is you. While moving from A to B, are you moving in the direction of current or opposite to the current? You are moving in the direction of current. That means you will write it positive. What you will write? I into R. What is the current? I1. Resistance is 4. Clear? Now, from B to C, you are entering the cell from the positive side. That means you should write it positive. Again, when you are coming from C to D, you need to complete the revolution. Now, when you are coming from C to D, you are again moving in the direction of current. That means again I1 into 1. Now, there is again a cell. You are entering the cell from the negative side. That means minus 10 is equals to 0. This is our equation number 1. You can simplify the equation. You can simplify the equation. Clear? In this side, if you solve in this side, can you tell me the name of the loop? Loop name is A, F, E, D, A. You are moving in this direction. A, F, E, D, A. Again, can you write? Resistance is 2. Current is I minus I1. Should I write it positive or negative? Should I write it positive or negative? Quick with the response. You are moving in the path AFEDA. AFEDA. Should I write it positive or negative? Quick. Negative. Okay. Negative. Okay. Okay. So two persons have responded. Ristia and this is Chichuni. Okay. Uh, is it your convention or the convention that I have told you? Which convention you are using? Because what I have told, if you are moving in the direction of current, then you should take it positive. If you are moving in the direction of current, then you should take it positive. From F to E, you are entering the cell from which side? From negative side. Then you should take it negative minus 4. Again, in this part, you are moving in the direction of current, then you should write what you should write plus 5 I minus I1. And again, from this side, you are moving from D to A and entering the cell from negative side, that is minus 10 equals to 0. This is equation number 2. Now you can form the equations and you can get the answers of whatever current you want. This is how you can apply Kirchhoff law. Moving further. This is electrical energy. Electrical energy, is a very simplest thing. You should remember the formulas that I have mentioned. I don't need to explain these things. This is simple formula. You can remember these formulas very easily. So I'm not going to invest a lot of time in here. If you know the electrical energy, then what will be the electrical power will be energy divided by time. Energy divided by time will be the power. So again, the T term will be cancelled out. And this is what power is. This is what power is. This is the simplest thing. I don't need to explain it. You need to remember the formula, take a screenshot and remember the formula. Now there is a question. This is again an important question. In your previous NEET exam that was full syllabus test on 24th January, 24th March, I think you have seen the question similar to this. Question says, if voltage across a bulb rated 220 volt and 100 watt drops by 2.5% of its rated value. Okay, so let's figure it out. The percentage of the rated value by which power would decreases. Question might seem a little bit difficult, but it's a very simple question. What is power? P is V square by R. P is V square by R. Now, if I write percentage change in power, it will be resistance is constant. It will be 2 delta V by V into 100. So percentage change in voltage is given as 2.5%. So you can write is 2 and percentage change in voltage is 2.5%. So percentage change in power will be 2 into 2.5 is 5%. Try to remember such type of question. These are very important. Ina, you are also saying negative. That means the convention you are using is the older convention that you have studied in your classroom. Okay, which part you want me to repeat? I think you want me to repeat this part now. Okay. Delta P by P is what? Fractional change in the power. For percentage, you need to multiply it with 100. This thing is clear. Now, in terms of V square, if it is written as something, I think you are confusing with this too. If it is something is like, suppose x cube, then percentage change will be 3 is the power that will come out and it will be delta x by x. This is how you can write the percentage change multiplied with 100. You can write the percentage change. So here, this was V square. So you can take this 2 out. Delta V by V is the percentage change into 100. This is the way we write the percentage changes. Resistance is constant, so we are ignoring this. Wheatstone bridge. Wheatstone bridge is again a very, very good thing. Okay. Why are we using the formula V square by R? Okay, this is again a very good question. Moving back, moving back, moving back. Okay, so here we have lot of formulas here. Okay. In the question is saying that it has some potential. It has some potential. And according to the question, resistance is there must be a resistance. Bulb has some potential, then it must have some resistance. Clear? If you change the potential, then current will also change. Very good, Deepak. If you change the potential, then current will also change. So that's why we are not using the second relation. That is I square R is not used. Why it is not used? Because we are not given with the current. We are given with the change in potential. That means there should be a term of potential. This term is not used because I is also variable in it. Because I is also variable in it. Because if you change the potential, I will also change. So I am using this relation because in this relation, only change in potential is given. But the resistance will remain constant. That's the case. That's why I'm using this relation. I think who has asked the question? Uh, mhm. Is it clear to you now? Why we are using this V square by R? Now, Wheatstone bridge is very clear. Very good. In balancing condition, in balancing condition, what is the balancing condition? When no current in galvanometer. This is the galvanometer. When there is no current in the galvanometer, then this is known as balancing condition. And what it signifies, the ratio of these two resistors, R1 by R2, is equals to R3 by R4. This is the Wheatstone bridge condition. And in balancing condition, there is no current in the galvanometer. There is no current in the galvanometer. This is the simplest thing. Now, again, moving further for the meter bridge. This is the most important thing that you should remember. This is how a meter bridge look. You have seen it in your laboratories. The representation is something like that. This is the left gap in which I have put a resistance box. This is the unknown resistance. This is the meter bridge wire. Of which material this wire is made? Can you explain? Can you know? Or how many of you know that which material is used to make the meter bridge wire? Anyone knows? This wire is made of constantan. Okay, someone has done. No, no copper, no aluminum. Listen, listen, listen. Constantan or manganese. Constantan or manganese. These are the two materials which are used to make the meter bridge wire. I think you know the construction, na? This is here a wire is placed. This is called as meter bridge wire. This length is 100 centimeter. These are the copper strips. These are the thick copper strips. Clear? Now, why it is made of manganese? This is sometimes asked why this wire is made of manganese. Because this manganese wire has low temperature coefficient. Why this manganese wire is used? Because it has low temperature coefficient. What is the meaning of low temperature coefficient? It means if you increase the temperature by many folds, the change in resistance will be negligible. Remember these things I am telling you. Remember this question. Why it is used of manganese? Because it has low temperature coefficient. Clear? Now, after putting these R and X, this is resistance box, this is known resistance. We know this resistance, this is unknown resistance. What you can do, you can move the jockey. This is jockey. You can slide the jockey on the wire, and at a certain point, you will see that there is no deflection in the galvanometer. And such point is known as null point. Such point is known as null point. This is the null point. And for a null point, it behaves at a Wheatstone bridge or balanced Wheatstone bridge. And in this situation, what will be the value of unknown resistance? This is the value of unknown resistance. X is equals to R, 100 minus L over L. This is L, this is 100 minus L. Okay, I will explain. I think you don't know much about meter bridge. So I will explain it. These are the punchlines. Take a screenshot and try to remember these punchlines. It will help you out. I will explain you a few things here. Okay, null point again. Okay, listen. Okay. Can you see me? Have you seen jockey in your classroom, in your laboratories? There is a jockey, which is a sliding pen. Okay. So when you slide after connection, when you slide the pen, this jockey from one end to the other, there will be a point at which your galvanometer will show zero deflection. The needle of the galvanometer will not deflect. And this point is known as null point. This point is known as null point. And the length of the null point from the positive end, this is the positive, this is negative. So from the positive end, the length of the null point is known as balancing length, is known as balancing length. So null point is the point at which galvanometer shows no deflection. Clear. Try to learn these things. I will come out on this, or you should remember, you can remember these things. These are the specially written punchlines by me. Now, I will tell you how to use meter bridge setup, how to solve questions. Listen, whenever you see a question, I am giving you a question. Principle of meter bridge is, you know that principle is balanced wheat stone bridge. Now, I will take hardly 5 minutes. So just be with us. Suppose there is a question like that. Okay. So this is what? This is some resistance R. This is some unknown resistance X. And this is wire AB. This is called meter bridge wire. This is a galvanometer and this is the null point. Let's suppose this null point is at 60 centimeter. Then this length will be what? Total length is 100 centimeter. This length is 60. Then this length will be 40. Clear? I think yes, very good. Now, how you can apply this relation? I am saying that just write the ratio of these two quantities, this one and the quantity and the value written opposite to it. So you can write R divided by 60 is equals to X divided by 40. That's how you should use the meter bridge. You shouldn't use this relation. You should not use, that's what my recommendation is. You shouldn't use this relation. This is the relation for the board examination only. Now what you should do, write the ratio of the opposite quantities. This is resistance R. This is the balancing length. Length opposite to it 60. This is resistance X and length opposite to it 40. R by 60 is equals to X by 40. You can calculate X here. Clear? Now there is a question. Okay. Should I do the question or are you getting late for your chemistry class? Quick. Should I solve it? It's okay. What does it mean? Should I stay or let's solve, sir? Okay, very good. Okay, if you support, I will definitely solve it. Okay, listen to me. A resistance wire connected in the left gap of a meter bridge balances a 10 ohm resistance in the right gap. Now I need to draw a diagram. Listen, you should be very quick in drawing the diagram of meter bridge. This is the meter bridge wire, left gap, right gap, and this is it. And it says 10 ohm resistance at the right gap. This is 10 ohm. And this is some unknown resistance. A resistance wire connected in the left gap. This is some unknown resistance X. At a point which divides the bridge wire in the ratio 3:2. What does it mean? That the galvanometer, the jockey, divides this length of the wire in the ratio 3:2. Clear? Now, they are asking me if the length of the resistance wire is 1.5 meter, which length they are talking about? Can anyone say which length they are talking about? This 1.5 meter is the length of what? Veena from YouTube, can you answer? Which length is this? This is the length of the wire. This wire length is 1.5 meter. This length is of this unknown resistance. What is unknown resistance? They have put a wire in this left gap, which has a length of 1.5 meter. Now, using meter bridge principle, you can write x over 3. I have told you now, x over 3 is equals to 10 over 2. So x is what? 15 ohm. Is it clear? This is the unknown resistance x. Then the length of the 1 ohm of the resistance wire is. Question is again very simple. Some of you might confuse with it. Now this X has a resistance of 15 ohm and length is 1.5 ohm. 1.5 meter has a resistance of 15 ohm. Is it clear? 1.5 meter has a resistance of 15 ohm. So they are asking me 1 ohm will have a length of 1.5 divided by 15. So that will be, is it clear? 0.1 meter. And 0.1 meter, can you identify out of these options which is 0.1 meter? I think B is the option which has 0.1 meter. I think you might have confused with this second part of the question. What is it? What we have calculated? We have calculated the resistance of this unknown wire. The wire has a resistance of what? 15 ohm. The length is 1.5 meter. They are asking the length of 1 ohm of the resistance wire. So I have used unitary rule, unitary method, or you can say what I would say, unitary method, you can say toffee rule. If 15 ohm resistance has a length of 1.5 meter, then 1 ohm resistance will have a length of this much. This is 0.1 meter. I think it is clear now. Okay. So we have completed a bulk of the portion of current electricity. In the next class, we will cover magnetic effect of current. Try to revise all these things and try to solve PYQs as much as possible. There is one more thing, that's potentiometer, which is left. I hope you can solve, you can understand it by yourself. I will share this sheet with you, share this PDF file. Okay, very good, everyone. So now it's time to say bye. Okay, we will end the session. Bye, everyone. Take your chemistry class and solve PYQs and inform me that you are solving. Bye, everyone. Bye.